Hey everyone, here's the continuation of this difficult titration problem. Where we last were was that because we are at the exact half equivalence point at 15 mils, this term goes to 0 because the base and the acid concentrations are equal in our case. So now all we have to do is figure out what the pKa is as opposed to the pKb. So what we solved for, before was the pKb of this, but the flip side of that. So the pKb, right, is the addition of a proton from water to ammonia to become ammonium. And then the flip side of that is ammonium acting as an acid, donating a proton to water. That process is related through the equation of pKa times pKb equals Kw. So, in essence, if we have the Kb from the reaction associated with ammonia gaining a proton from water, right, this reaction here, we could also easily calculate Ka for the process by which ammonium donates a proton to water to produce ammonia and the hydronium ion. Now recall, none of these, right, are the titration with the HCl. But in order to answer part, E part 2, at this point, right, the HCl that's been added is gone, and that will be true up until the equivalence point, right? So every bit of HCl that's been dripped in is used up in the reaction with NH3. At half the equivalence point, we've reached the point at which, the base and the acid forms are equal because half of the ammonia has been converted to ammonium. So at that point on the titration curve, right, we're in this buffer region, we can determine the pKa of our weak acid through this relationship. And as you recall, in the, above, in the previous problems, we found out that the Kb was a certain number. So pKa is equal to 1 times 10 to the negative 14, right? That's our value for K. Oh, I'm sorry, I misspoke here. The Ka times the Kb is the Kw. So the Ka is what we solve using this equation, not the pKa. So we plug in now our value for Kb, which we solved before, which was the 1.74 times 10 to the negative 5. And what we end up with is a value for our Ka of 5.75 times 10 to the negative 10. So that is our Ka. And because we are in a scenario where, going back to the Henderson-Hasselbalch equation, we are in a scenario where the pH equals the pKa. We're now simply going to figure out the pH by taking the negative log of this number. Remember, the p of anything is the negative log of that thing. So the pKa is the negative log of our Ka value of 5.75 times 10 to the negative 10. Giving us a value of 9.24. Looking back at our graph, this is exactly where we expect it to be, right? Above 7, and 9.24 definitely seems to be a very reasonable answer. Now to finish the problem, determine the pH of the solution in the flask after a total of 40 mils of acid have been added. So we determined before, right, that 30 mils was our equivalence point. So 40 mils is 10 additional mils beyond that. So the secret to answering this part of the problem is again realizing that you are now past the equivalence point. At this equivalence point, there is no ammonia left for the HCl to react with. So that additional 10 mils of HCl is simply just H plus being added to solution. So we take a look at our molarity of 0.0120, and we write it as the molarity, as moles per liter, and we're going to multiply by that additional 10 milliliters over. Notice, remembering that 30 was the neutralization point, so now at 40 we have an additional 10 liters, or 10 milliliters of HCl added. When we multiply this across, we find that we have 1.2 times 10 to the negative 4 moles of H plus that are now just hanging out in solution. Of course, what we need to do to figure out the pH is calculate its molarity. And here again, you have to be a little bit clever. Let's go back to the original problem. In the original problem, we had 20 mils of the NH3, and at this point, we have added 40 mils of the HCl. So in order for us to accurately calculate the molarity at this point, we have to add those two volumes together. So 20 mils plus 40 mils gives us 60 mils of our new solution. And dividing our moles by 60 mils in liters, right? 0.06 liters. We end up with a molarity of 2.0 times 10 to the negative 3 molar H plus, or HCl. And I believe the original question asked us to solve for the pH. So at this point, right, we take the negative log of that answer to give us the pH. Because, right, the pH is the negative log of that molarity. And we have a pH of 2.70. So that concludes this problem. Just to wrap up, in order to solve these problems, I highly recommend drawing out titration curves, even if it doesn't tell you to. Big takeaway points are, if you are working in the buffer region, if you're asked about the pH in the buffer region, we use the Henderson-Hasselbalch equation to get the answers we need. If you are after the equivalence point, then you would use any additional added acid or base just simply as that moles of H plus or OH minus, depending on what the titration is. And then lastly, in order to figure out the equivalence point, you have to write down the balanced chemical equation. In our particular case, it was 1-to-1, although there's certainly no guarantee that it's going to stay that way. Whoops.